we're going to continue. Sorry for the delay. The next Juan Chen, which is a master's degree student, and
Thank you everyone for attending this talk. Okay, we will present an introduction about optical, digital optical methods and its application in robot navigation assistance. By nature, vision is the input of many information sources such as shapes, colors, texture, distance, movement, and many others. Because of its versatility, current advances in technology have required the development of artificial vision systems. Some applications where the vision systems has an important role are three-dimensional scanning, facial recognition, vehicle navigation, and the technology advances, as well as the increase in scientific community on vision, have motivated new applications based on vision systems. For instance, augmented reality, theoretical and practical problems. Conventionally, a vision system is addressed from two different viewpoints. On the one hand, output of the system, for instance, cameras, projectors, and light sources. On the other hand, digital computers are used only for the data processing of optics, and optics for processing tasks. The functions of optics, such as synthesis of reconstruction of holograms, can be performed using computers. They were the earlier applications in this sense. In contrast, the classical approach, the performance of vision can be increased using the optical, the high resolution and powerful the optics elements for computational purposes. Responses. And it is well known that computers are very easy to reconfigure and modify, being they ideal for adaptive applications. The successful application of this approach is here in applications such as opto-digital image correlators, real-time, for example, the motor cameras, the zoom is performed from two viewpoints. For optics, where the optical elements are modified to modify the field of view, and digitally by improving the captured images. Then the fusion of these two approaches generates a hybrid digital optical system which has a better improvement. In our laboratory, we have addressed different applications using opto-digital approach. For instance, image restoration presented by Enrique in previous talk, two-dimensional and three-dimensional object recognition, three-dimensional scanning, optical tints are presented. First, Obed Rios will present an extension of image rectification method useful in stereo camera systems for 3D environment sensing. Next, Juan Chen will present his results when estimation are implemented. Okay, thank you.
Well, hello everybody. My name is Obedan. First of all, I am working on 3D imaging. This topic, we work this topic here in Citedi, 3D imaging. So nowadays we have 3D imaging applications, and that is important because we can apply 3D imaging technology for object preservation. We can apply 3D imaging for manufacturing and even for medicine applications. Regarding the imaging technology, we have a different approach how to do how to get all the objects in the world in your computer. In this case, digitizing the object. So the disadvantage here for these techniques are expensive and very slow. And we have another kind of technique. This kind are structured light techniques. The lower cost and faster because it's like applying several lasers through the object and get the estimations in our computers. And we have another kind of approach, which is a stereo vision. So stereo vision, and then we can reconstruct the object in our computers using several images. The disadvantage is a camera calibration is a critical part for these kind of systems, reconstructed in totally. We are interested particularly on structural light methods. Structural light methods, there are different. We have only one shot to reconstruct the 3D object, and we have continuous patterns, and we have indexed grids. But we are interested in using multiple 3D object from the 3D world using a grid model. And this grid model is processed by a projector and is projected through the surface of the object, and we have finally the object reconstructed. And this is the classic process using fringe projection. And well, these systems involve the triangulation problem, but we want to explore first the stereo systems and the triangulation problem. So first we have here in this figure, figure A, we have 2 cameras, and the problem is here is given a point in both images, which point corresponds to the 3D world. So how to find this? So we have infinite points, and we search through the lines to the infinite. But we have another kind of solutions for this. We have a rectification image for stereo systems. So we apply a property projective transformations, and with adequate proper projective transformations, only we trace horizontal lines and we search for horizontal lines. And this is a very fast a fast way to find points through the images. So this is a proposed approach. We use a camera projector. So we are going to do is a rectification on camera and projector systems. So we have these systems, and because we use a proper projective transformation, we know only in this case, for this example, the y-axis. We know the y-axis, but we want to estimate the other axis. So what are projective transformations? Okay, let's consider this space is Rn, and when we we apply transformation for projective space, we have options are in this case A greater than R plus 1. We are going to have a vertical rectangular matrix, and we are going to obtain a smaller space but bigger than Rn. But if we have greater space, in this case, we are going to have another kind of matrix, which is in fact a projective transformation. But the transformations we are interested in is when R plus 1 and the matrix are the same. So what are the applications for projective transformations? So one example for projective transformations are an object that relates those points and how to relate those points into different planes. So this case, this object mathematics is called homography. The homography is a matrix in homogeneous space, which is R rectangular, R not singular, R invertible. So for example, to solve this problem, we can apply a least squares approach. which is a direct linear transformation approach. But what if we have noise in both images on both planes? So we need to apply estimations. So in this case, estimated points, and we may apply an algebraic distance error cost to estimate the homography. But maybe we have the true points and we have the estimate points, and we want to transform or get the transformation from the true points to estimate points. Well, we use the symmetric transfer error to estimate the homographies using that. The functions to estimate these errors are geometric distance cost. To estimate homographies are iterative, estimated points, and we find homography. Some applications for projective transformations are perspective correction. We give 4 points for the original image, then we apply a projective transformations, and then we have distorted image corrected. And we have coordinate transformations between devices. So what if you have a set of points in the real world? How to map these points in your computer or another device? Could be CNC or another count device coordinate. The other applications for projective transformations are camera calibrations. This is a critical part for
Hello everyone. I'm here to present one of the work that I'm doing for my degree, which is creating a 3D model using 2D views captured by robot navigation assistants. How do I since I'm what the name implies is creating a single image using multiple smaller images, let's say. One of those smaller images, since it's using the projective transformation that Obe was talking about, where we're gonna move the image plane into a 3-dimensional space. Let's say in this example, in order to start the image stitching process, we're gonna identify correspondence object between the images. In this case, I'm using this object. We want to find the coordinates in the images. In this case, we use the 4 coordinates of the monitor. Using the direct linear transformation method, we know we can estimate the homography matrix using the 4 points of the coordinate. And once the homography matrix is known, we can do the reprojection on those images on the same coordinate in the 3D space to form a similar result that's shown in these images, where we superpose the first image on the second image, so we get a better image view. This image is in the 3D space, but we can still view it to this, where we can see the indoor scene in the 3-dimensional space, where we can see the wall of the laboratory. In this case, this is used mostly in texture mapping and 3D models, which is one of the work that I'm currently doing for my degree. So I was saying in a little bit, we need to identify this object or this rectangular object. In order to do that in Robot Assistant, I used a different method to detect the shape. There we go. To do that, I start use shape. So in order to visualize it better, I want to change the coordinate system into a parallel coordinate, where we can see this kind of the higher intensity of the parallel coordinate, we can see it's a representation of the line of a line in the image that it is getting. In this case, it can be a line from this one or this one and this one. So in order to validate that this method is working correctly, we the information about the camera when I wanna the position orientation of the camera. So I use a square radial checkerboard pattern in order to detect. This is the pattern I'm using. So I wanna change this image into a parallel coordinate using hook transform, so I can detect the highest intensity of the image in order to get the representation and the diagonal one, so we can get the intersection, which is the center point of the pattern. And using the second form of the hook transform, we can get the intersection between these parallel lines in the x axis and the y axis. Then we can estimate the tomography in order to use that for the camera calibration. So this process is to find and we have a different problem. So we want to predict where the corresponding point is on the next frame. So in order to do that, I use optical flow when I want to detect the direction where the corresponding points start moving, and which position is going to be next. It's what I want to start predicting. So in order to get the time, the different frame, the difference of the frames. So on the next slide, I'm presenting a little bit how the robot will start visualizing the object. So we start doing the process for the image staging. This one. So on the left, we can see how the movement in every pixel. Since the camera start moving, every pixel is gonna move. So we can see a little bit more noisy the robot. So in my work for the degree, I wanna combine every method that I show in here, the hook transform, the optical flow, and the image staging process. So I wanna combine all this method into a better application. So it's gonna be my future work. And well, in summary, we presented a little bit of different topics. First most, performance of visual system that can be increased if the optical and computational aspects are integrated into a single optical system. A structure-like methods was shown, so we can use that in 3D scanning. Alternative performance was transformation is important due to many applications in computer vision, as shown. Some principles in 2D views were constructed for 3D scenes by image stitching that was presented. The hook transform was used to detect the corresponding points. And finally, was the optical flow to predict the movement of the objects. Thank you. That's all.
Okay, I have a question.
Yes.
For the case of 3D digitalization of objects, which is the frame rate that these systems can solve?
Well, I didn't test it yet. The frame rate. Do you mean in case of the terms of time? In this case, we are testing the fringe. The fringe is we are taking different steps, and we take several images with different shifts, and it depends of the skills of the operator. And I believe is one of the principal weakness of that method. And find those methods that doesn't require a lot of computational resource. So I believe that's it.
So the most time-consuming part is like the projection, not
it's
so much the processing by itself.
Yeah, it's the part of calibration process, or in the part of getting the image. I believe this is.
Technical methods are used to solve state-of-the-art problems, not like the Hue transform. But the Hue transform will also be like limited to the type of objects that you will see, no?
Yes.
Any reason why you choose this one to detect the objects in the scene? I mean, maybe there's a constraint on the type of environment where you will use the robot, no? But the Hue transform, I think, is a very good tool, no? But only works in certain scenarios.
But for main reasons, at least.
So, thanks to the speakers.